Welcome back to Quick Hits in Laboratory Medicine. I'm Rob Fitzgerald, and the next 5 minutes or so we're going to talk about determining if your patient's results are getting better or getting worse, or if the variation is actually just due to analytical variation in the laboratory results. So are my patient values getting better? So have they changed, or is that just a statistical variation in the imprecision of the laboratory test? So, for example, you're taking care of a patient, and on day one, their sodium is 120 millimoles per liter. They're hyponatremic, and on day two, you've done some intervention, and you want to see if they're getting better. And so you measure their sodium again, and on day two, it's now 126. The normal range for sodium is 135 to 145. So it seems like it's headed in the right direction, but that could also be due to analytical variation. And one of the problems with laboratory medicine is that we don't report error bars. We just report a sodium as 120, and it's really up to you to figure out if it's getting better, if it's getting worse. And unfortunately, we don't give you all the data to figure that out, and you really have to contact the lab if you're concerned about whether or not the measurements are changing or if they're actually the same. And one of the ways that we understand that in the laboratory is by measuring quality control samples. So these are samples that we measure every day on a routine basis, and so we have a history of, and we understand what the variation is. So in our quality control monitors, we understand what the mean should be, we understand what the coefficient of variation should be, and that's really determined by the standard deviation. And so the thing to remember and the take-home message is, if your lab values have changed by at least 3 times the standard deviation, then they're analytically different. And if they're analytically different, then you can start to talk about whether or not they're biologically different. But if they're not analytically different, then you can't make any assumptions about the biological difference or if you're making your patient better or worse. And so how do we do that? We run these quality control samples, as I said, every day. And so this is what we would call a Levy-Jennings chart. And on the x-axis, we have dates. So that would be different days that we're running this test. And on the y-axis, this would be the mean is typically plotted in the middle. And then we plot it according to standard deviations. And so the first dotted line would be 1 standard deviation above. Second dotted line would be 2 standard deviations above. We make the assumption that these are Gaussian distributions, and so inner 95% is plus or minus 2 standard deviations. So 95% of our values should fall within that plus or minus 2 standard deviation range. And so we run that every day. We get a mean and we get a standard deviation. And in this case, the standard deviation for sodium, probably one of our most precise assays, is about 0.5 millimole per liter. So it's a very precise test. Again, looking at quality control charts, this is again a Levy-Jennings chart, and this is what it normally looks like. We've got scatters jumping up and down. If we plotted that data as a histogram, it would look exactly like this. And so here we have a Gaussian distribution. Our control limits are plus or minus 2 standard deviations. So this little corner up here would be 2.5%. This lower corner would be 2.5%, and in between is the 95%. Of the values in a normal distribution. So what's happening here is everything's fine, we're reporting patient results, all of a sudden something happened, and now we are dropped down, and our quality control is falling outside of our control limits. These are failing quality control, and so we need to fix this. So the technologists would fix this before reporting results. So your assumption is that as a clinician, these are going to be taken care of in the background and you're not aware of them. We're only reporting results when the quality control looks like this. If you summarize this data, it would look exactly like this. And so basically this is a mean shift. So maybe the calibration has gone bad or the quality control sample degraded or something like that. We would have to fix this before we could report patient results. Further on, we come back, we are now back at the mean, but we're bouncing around quite a bit, and this is an imprecision problem. So here we had an accuracy problem, and here we have an imprecision problem. And in the laboratory, we're going to troubleshoot those differently. But the bottom line is that we run quality control every day on every analyte, and it does give us an idea of the precision of the assay. So back to our original question. On day 1, our sodium was 120. On day 2, it was 126. And we wanted to know, is the patient getting better or worse? So that difference is 6 millimoles per liter. You would have to call the lab and say, what is the precision of that test? And we would tell you it's probably about, between 0.5% and 1%. And in fact, the standard deviation for that test near 126 is 0.5 millimole per liter. And so you would multiply that standard deviation by 3, which is quite simple. So 1.5. So 1.5 is a lot smaller than the difference of 6. And so the imprecision of the test is plus or minus 1.5. That's 3 times the standard deviations. Both of these values are varying, so it comes out to be about, it's really 2.7, but we just sort of rounded up to 3 because of other assumptions that we're making. But essentially, if lab tests have changed by 3 standard deviations, then they're analytically different. And if they're analytically different, then you can start to make some determinations about biological differences. But if they're not analytically different, then you can't say anything about biological difference. Thank you.